All right, so let's go ahead and continue talking about finding relative or local extrema. So we're still finding local or relative, whatever you want to call them, extrema. And just as a reminder, that just means if it's a maximum or a minimum, that means it's just higher than, if the maximum is higher than everything around it, but it might not be higher than everything on the surface. If it's a minimum, it's lower than everything around it, but might not be lower than everything on the surface, right? It's locally a maximum or minimum, but maybe not globally or absolutely. We'll talk about global extrema maybe today, but definitely next week, if not today. Also, I should ask, when is your first midterm? This upcoming Monday? Oh, okay. Well, then we should definitely talk about. Oh, actually, I should look and see what's on the first exam. Let's go back and look at that real quick, just to make sure we're all thinking about what's going to be on the first exam. What's on your first exam? Maybe we're going to change what we're doing today. Let's see here. I should have looked more closely at that. So, let's see here. Pardon me, one moment while I double check here what's going on. Oh, I'm looking in the module for this class, not the module for your actually class. Sorry. One second. Let me look at the right class at actually 17C, not the Co-17C class. Smooth. And let's see. Sure. So what does it say here about your first exam? Oh, for topics, see material for midterm one. Okay, let's take a look. Material for midterm one, you have to download. Okay. Let's see what it says here. So section 9.1, 9.2, 9.3, 9.4, 9.5, and 9.6. So for 9.6, be able to find critical points in terms of their local maximum or saddle, and also optimization. Doesn't say anything about absolute extrema though. So like that's where you do extrema on a bounded region. So I don't think we'll talk about that today because it doesn't seem like it's going to be on your exam on Monday. All right, cool, good, good. That's what we're going to do anyway. So let's look at some more examples. Let's say we have the function f of x comma y equal to 2x squared minus y squared plus 4x plus 10y plus 1. And again, we're trying to find all the critical points first. So the first thing you're going to do every time in this process is first find your partial with respect to x and your partial with respect to y. So my x partial is going to be 4x plus 4. My y partial is going to be negative 2y plus 10. And we're going to set each of those equal to 0, just like we would have set the derivative equal to 0 in 17a when we're finding critical values. It's just now we're trying to find solutions to both of these equations. So far, it's been not too terrible. In this first equation, we're going to get x equal to negative 1. In the second equation, we're going to get y equal to positive 5. And so these two together form our only critical point, negative 1 comma 5. We'll definitely get some examples that have multiple critical points here in a minute, but I just want to make sure we're set on how this all works. So let's see. So now we have to classify. To classify it, right, because we don't know if it's a maximum, a minimum, or a saddle. So we're going to calculate this capital D thing, this determinant of the Hessian, which is again your fxx, your second partial with respect to x, multiplied by your fyy, minus your mixed partial fxy, and that part is squared. So let's see. So we're going to find all of our partials. So fxx, I can see that fxx is going to just be positive 4. Fyy is going to be negative 2. And fxy, just like last time, is still going to be 0. So in this case, our d value is negative 8. And when d is negative, which it certainly is, we're done. That automatically means we have a saddle. Um, this idea, by the way, so I want to point out this idea is going to actually come back around when we start talking about the next stuff, which is the solving systems of linear differential equations. We're going to be finding some determinants of some 2 by 2 matrices, and when we get a determinant that's negative, it's going to mean that we have a saddle in a somewhat different context, but still very similar. So this determinant of this 2 by 2 matrix we did right over here being negative, that concept kind of holds throughout the course. Let me just show you two, just so you all can, I think it's good to see what these things look like. So let me show you what it looks like, not by drawing it, but like actually showing you a nice, lovely graph here. So our function was z equal to 2x squared. Whoop, I'm not typing anything. 1 second here. Sorry. Z equal to 2x squared minus y squared. And really, the 2x squared minus y squared is going to give it to you all. That's definitely a saddle right there. You can kind of see opening one way, opening upward one way, opening downward the other way. And if we then add in the other pieces, it's just going to shift a little bit. We've got a plus 4x, a plus 10y, and a plus 1. And so you can't quite see the whole thing because we've moved it around, but if you zoom out, you can kind of start to see, oh yeah, there's the whole saddle shape. A downward opening parabola in one direction and an upward opening parabola in a different direction. That's kind of the entire nature of a saddle. And again, literally called a saddle because it looks like a saddle that you would put on a horse or a saddle that you would climb over on a mountain, right? Good name. It's also called like a hyperbolic parabola or something. It's a saddle. It's called a saddle. Okay, let's look at some more examples. I think we've got one more easy example, and then we're going to get some harder ones. Yeah, this next one. Oh no, okay. We start with the hard ones here. Cool. So let's look at this next example, which is going to be much more challenging to find all of the critical points. So our function is x to the fourth plus y to the fourth minus 4xy plus 2. And here's something that I think is worth making note of, even though it's not really talked about. This function is symmetrical in the variables x and y. What I mean by that is if you were to replace every x with y and every y with x, you'd still have exactly the same equation, right? I'd have y to the fourth plus x to the fourth minus 4 times y times x plus 2. Still exactly the same. When that's the case, I want to say always, but I'm going to say almost. Almost always, every critical point is either same x value, same y value. So like 2, 2, 3, 3, -5, -5. Or if you get 1 comma 7, you also get 7 comma 1. So if you see that kind of symmetry, you just want to keep in mind, oh, I'm probably going to get things that are like the same on either x and y, or they match with another one that has the opposite things. Let's see if that's actually true. So we're going to find our critical points. So we're going to find our fx. It's going to be 4x cubed minus 4y equal to 0. And fy should look similar. It's going to be 4y cubed minus 4x equal to 0. So here, we're not just immediately getting an x value and a y value. We're actually going to have to do a little bit more work to figure out what points make both of these equations equal to 0 at the same x and y coordinate. Typically, what we do is we take one of these equations and isolate either variable. So in this first one, I'm going to isolate y. So I'm going to say 4x cubed equals 4y, and then x cubed equals y. And then we're going to substitute y equal to x cubed in, and I'm going to simplify this one a little bit too. So in this equation over here, I would simplify this as, no, I wouldn't. I'm going to just factor out a 4. I don't love that either, but fine. 4y cubed minus x equal to 0, or really just y cubed minus x equal to 0. But then what I'm going to do is I'm actually going to substitute in y equal to x cubed. So what I'm really going to have is x cubed cubed minus x equal to 0. So that's going to be x to the 9th minus x equal to 0. And you can either, I mean, we will solve this, but I want to point out, I bet you could guess some answers to this equation. What's one easy solution to this equation? 0 for sure. What's another one? I just said it. 1, right? 1 to any power minus 1 is 0. And another one that's going to work here is also -1, because -1 to the 9th is -1, minus -1 is going to be 0. So when you have just powers of x or powers of y and nothing, no coefficients really, usually zeros and ones make up most of your answers. But let's actually solve it. If we're solving this, I'd factor out an x. Oh, I know what I want to point out. Here's why I want to point this out. If you go in this other direction, which don't write this down, if you said like x to the 9th equals x, and then we say we divided both sides by x, which is not what we want to do. But if you divide both sides by x, you maybe say, oh, x to the 8th equals 1, and then you might miss out on 0 being a solution. So really, 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 I want to emphasize We don't typically want to divide by variables with some small exceptions, but really it's usually a route to missing at least one solution. So not this. Instead, we factor, we get x to the 8th minus 1 equal to 0. We could factor this more if we wanted to, as x times x to the 4th minus 1 times x to the 4th plus 1, and then factor that more as x times x squared. Oh my gosh, this factors a lot. I should be smarter about this. I shouldn't be doing all this factoring, but it does factor a whole lot. And then you can see, oh yeah, I get x equal to 0, I get x equal to 1, I get x equal to -1, and these two pieces don't really give me any other real solutions. We're only halfway done. No, we're not even halfway done. We're like a third of the way done because we haven't found any critical points yet. We have found the x coordinate of a bunch of different critical points, but we also need a y coordinate to go with that. Fortunately, we know that y is equal to x cubed. So knowing that y equals x cubed, x equal to 0 is going to give me y equal to 0. X equal to 1 is going to give me y equal to 1. And x equal to -1 is going to give me y equal to -1. Notice the thing I said was going to happen happened, right? We see that for this equation, which is symmetrical in x and y, all of our critical points have the same x and y value. We don't have any of the other type. Okay, so now we're going to do the usual thing, but in this time, instead of just getting like a number times a number minus 0, we're actually going to get some second derivatives that have variables still left in them. So we're actually going to have to like plug in each pair of points. So here, our fxx is equal to, let's see, the derivative of fx with respect to x is going to be 12x squared. Our fyy is going to be 12y squared. And our mixed partial, fxy or fyx, is going to be -4. We're going to use those pieces and then calculate d. So our d is going to equal 12. Oh, and so here's a good word of advice. Don't multiply this out. Leave it as 12x squared times 12y squared minus -4 squared. You might multiply out the -4 squared, but like especially the fxx times fyy part, it's really a disadvantage to multiply those out. Like I don't want to say this is 144x squared y squared, because later on, when I'm trying to figure out if something's a maximum or a minimum, I'm going to want to know if my fxx was positive or negative. So I think it's worthwhile to leave this unmultiplied out. All right, so now we're going to check each of our 3 critical points here. So first we're going to plug in 0, 0. When we plug in 0, 0, we're going to get 0 times 0 minus 16, which is negative. And when it's negative, what do we have? Saddle every time. So if your d is negative, saddle. So that means 0, 0 is a saddle. Okay, let's plug in 1, 1. We plug in 1, comma 1. I'm going to get 12 times 1 squared is 12. 12 times 1 squared is 12. Minus 16. We don't care what the value actually is. You don't need to say 144 minus 16 is whatever it's equal to. You just say it's positive. And when it's positive, what do I have to now do? Right. So what I really want to make sure you aren't saying is, right, if it's positive, we don't know yet what's happening. We don't, but we know it's not a saddle, but it still could be either a maximum or a minimum. So then we're going to check either fxx or fyy, and you're going to say, oh, cool, our fxx is positive, which means we're concave up, which means we have a minimum at 1, 1. I really, really think it's worth taking the second to at least think about the concavity, if not actually drawing the little concave up thing. To me, that just reinforces, oh yeah, positive second derivative, concave up, and concave up means you have a minimum right there. Similarly, if we plug in -1, -1, we're going to get 12 times 1 times 12 times 1 minus 16 again. This is also positive. Our fxx is also positive, so we also have a minimum. So also a minimum at -1, -1. So this function, this surface, has 2 minimums and 1 saddle point. I do think this one's kind of neat to look at, in addition to just, I think it's good to look at these things in general. So this one looks like, let's see, let's do that. Maybe not. Cool. It was x to the fourth plus y to the fourth minus 4xy. That looks crazy. Not really. Plus 2. And I should recenter my picture here. There we go. Kind of looks like a pair of pants. Like, right? You got your two minimums down there, and then in the middle, you've got your saddle point. Kind of cool. So yeah, just like we expected to see. Let's look at some more examples. I might have you guys try this next. Oh, that's all I got right there. Cool. Let's go over here. Yeah. Yes.
So you're only using XX to see whether or not it's that minimum point?
Yes, or maximum. Here's what's happening. Technically, you could use either one. And here's why. Looking here, right? So this D thing we're calculating is going to be something times something, and then always minus a positive number. So if these two somethings have opposite signs, right? If fxx is, let me go back here, right? If fxx and fyy have opposite signs, like one's positive and one's negative, then that product is going to be negative, and then you're subtracting out something positive, so it's going to be even more negative. So I'll say this again in a different way. If these two things have opposite signs, you have to have a saddle because you have a negative number minus something making it more negative, giving us a negative number. So the only way that we don't get a saddle is if fxx and fyy have the same sign. They're either both positive, and I'll say that's a necessary requirement, but it might not be enough, right? These might both be positive, and this might still be negative enough to overcome it. But for sure, to at least have the chance of having a maximum or minimum, fxx and fy have to be both positive or both negative. And that's why we're only checking one of them. Because we know if we're in the situation where you have a D that is positive, meaning we have a maximum or minimum, we already know, oh, fxx and fy had to be the same sign. So we're just going to check one of them because it's the same sign as the other one. So more broadly, you can check either one. You can check fxx or fyy. Let's look at another example. Yeah, let's do that one. Sure. Yeah, okay, that's a good one. Okay, cool. So let's look at, oh, I should look over there too. I'll do that in a minute. So f of x comma y equal to 3x cubed plus x. Oh, thank you. Plus xy squared minus 9x squared minus y squared. Now I want you all to start off just by finding your fx and your fy. Oh, sorry. Didn't mean to do that. Yeah, question.
It's positive.
Uh-huh.
So to take the second derivative, so that makes me take the second derivative of either x or y.
Which we've already done because it's in the equation for D. Right, but so yes, and I'll say, but I'm not even really doing that because I'm just saying. So like here, when I plugged in one, like here 0, 0, I didn't care because it was negative, and a D that's negative gives me a saddle. Here for 1, 1, I plugged. And this is again why I said we don't want to multiply out the fxx and the fyy. So when I plug in 1, 1, I get 12 times 1 squared. That's my fxx. There's my fyy. There's my fxy squared. I see that D is positive, so then I look back and say, oh look. There's my fxx with that point plugged in right there. My fxx is 12, which is positive, so we're concave up, so we're a minimum. You can do more work, but you don't have to do more work. You're welcome. let's take a look here, see. So I will tell you this one, finding the critical points is a little bit harder. My fx is 9x squared plus y squared minus 18x. Ooh, that looks gnarly. And my fy is 2xy minus 2y. So I don't know how challenging your instructor is going to make these questions. There's some decent ones on this here. I do find interesting. Okay, we might have to talk about that after all. So here's what I would say in general. When you have two partial derivatives and you're trying to find the critical points by setting them equal to zero, you want to try to deal with the easier looking equation first. And in my mind, that's the second one. Because I can see in the second one, I can factor out a 2y from this left side of this equation. So I'm going to deal with this part first to try and help me. So I'm going to have 2y multiplied by x minus 1 equal to 0. So what are the values that make this equation equal to 0? Well, either y equal to 0 or what? Say it again? Right. Okay, here's a really, really, really important point of clarification. 1 comma 0 is not a critical point. To be a critical point, that point has to make both partial derivative equations equal to 0 at that point. So if I plug in 1 for x and 0 for y, sure, this equation is going to be 0. If I plug in 1 for x and 0 for y, I'm going to get 9 plus 0 minus 18, which is negative 9. So don't fool yourself here. We're getting to each of these is like half of a critical point. I've got y equals 0, and I'm going to find the x values that make the other equation 0. And then I've got x equals 1. I'm going to find the other values, the y values that make the other equation equal to 0. Or in other words, we're going to take each of these halves of critical points and substitute them back into the other equation to then figure out what the other variable has to be to make it equal to 0. So if we plug in x, let's do x first. X equal to 1 into this equation, we're going to get 9 plus y squared minus 18 equals 0. Or let's see, we're going to have y squared, 9 minus 18 is minus 9 equal to 0. And you can either add 9 and square root or whatever. You're going to get y equal to plus or minus 3. So we actually have two critical points from x equal to 1. Our two critical points are 1 comma 3 and 1 comma negative 3. It's certainly okay to write it as 1 comma plus or minus 3, but I'm trying to really emphasize here the fact that we have two different critical points. Yes. When you say use the second one to find the critical points, what do you mean precisely? Well, so we don't have that kind of equation in this situation. That was the previous one. So in this one, there's not a nice way of like writing y as a function of x here. Yeah, not really. Yeah. So yeah. I mean, you could if you wanted to like take this first equation and write y squared equals 18x minus 9x squared and then plug in x and get y, but it's kind of the same work. I would say the thing we did in the previous one feels like more work to me, kind of, because like you have to find what y and x are in terms of each other. Here, I feel like this is kind of nicer in that we're still getting an x value and a y value, and then we're just plugging those values back into the other equation to get the corresponding values that work there. So let's go ahead and plug in. In fact, why don't you all plug in y equal to 0 and solve for x? So if y equals 0, you're going to take this equation and write down what it is equal to 0, and then try to find your solutions. And you should get two solutions. So those are the other two critical points I'm getting, right? I've got 9x squared minus 18x equal to 0. I factored out the 9x to get 9x times parentheses x minus 2 equal to 0. So letting y equal 0, I end up getting either x equal to 0 or x equal to 2. So my other two critical points are x is 0 and y is 0, or x is 2 and y is 0. So we have four whole critical points here. You don't need to do this if you know you're right, but you could go back and plug in any of these critical points to each equation, and both equations will equal 0. If I plug in 0, 0, I get 0 plus 0 minus 0. And if I plug in 0, 0, I get 0 minus 0. If I plug in 2, 0, let's see, if I plug in 2 for x and 0 for y, well, I know plugging in 0 for y is going to make the second equation 0, right? I get 2 times 0 minus 2 times 0. If I plug in 2 for x and 0 for y, 9 times 2 squared plus 0 squared minus 18 times 2 is 9 times 4 minus 36, which is 36 minus 36, which is 0. So every pair of xy that makes up a critical point should make both partial derivatives equal to 0 when you plug in that critical point. All right, and now for the testing. So we're going to calculate capital D. It's going to be, so our fxx is going to be 18x minus 18. Our fyy is going to be 2x minus 2. And our fxy is going to be 2y. Our fyx is also 2y. It's not a bad idea to check that your fxy and your fyx do match, because they should match. All right. I think it might be helpful to label these. Just as a reminder, this is our fxx, this is our fyy, this is our fxy squared. Because then later on, after we plug things in, we'll know like what we're looking for. So let's go ahead and plug in 1, 3. Let's start with, let's make sure 1, 3. So plug in 1, 3. So if x is 1, I'm going to get 0 times 0 minus 6 squared. Definitely negative. So we get a saddle. In fact, the same thing's going to be true if I plug in 1, negative 3. If I plug in 1, negative 3, I'm going to get still 0 times 0 minus, now it's going to be negative 6 squared, which is still going to be negative 36, which is still negative, meaning I get a saddle. Okay, and then the other two, if I plug in 0, 0, let's see, we get 18 minus, sorry, we get 0 minus 18, so negative 18 times negative 2. Notice that the way I'm writing it is going to leave very easily, it's going to leave words. It makes it so it's easy to see what fxx is. Right? I'm not multiplying this out and saying it's 36. I'm saying it's my fxx value, which is negative 18, so my fyy value, which is negative 2, minus 0 squared. So that's going to be positive 36. And then we see that our fxx is indeed negative. So we know we're concave down. So we have a maximum. So we have a maximum at 0, 0. And then in a similar way, if I plug in 2, 0, let's see. Now I have 18 times 2 minus 18, which is 36 minus 18, which is positive 18, times 4 minus 2, which is positive 2, still minus 0 squared. This is also going to be 36, which is greater than 0. But now my fxx is a positive number. So fxx is positive. That means I'm concave up. That means we have a minimum at 2, 0. Let me show you that because again, I think I like looking at the pictures. So here's the picture of this thing graphed, but you can't kind of see all the points. So we can certainly see our relative maximum at 0, 0 right there, but we can't see any of the other points. We got to zoom out. So we zoom, ooh, wow, ooh, interesting. So, okay, I can kind of see the saddle there. So you know what I could do if I was being smart about this? I could plot all the points, right? I know that I can plug in 0, 0 for x and y and get the point 0, 0, 0 plus 0 plus 0 plus 0 is 0. Oh, look, there's that point that we said was a maximum. And now it's going to be hard to do, but we do the other one. So what was the other one? We have 2, 0. Okay, now I have to think. We plug in 2 for x, we're going to get 3 times 8, which is 24, minus 9 times 4, which is 36. So 24 minus 36 is negative 12. And we probably can't see that point because we haven't zoomed out enough. Where are you? Oh, it's somewhere. Oh, there it is. You can kind of see. So look, but now things look crazy. So anyway, that's kind of the idea. And then certainly you can see there's a saddle right there. If we plug in, like, say, I think it was 1, 1. Was it 1, 1? No, it was 1, 3. Ooh, 1, 3, 1 comma 3 comma Deesh. I should have been smarter about this. 3 plus 9 minus 9 minus 9. 3 plus 9 minus 9, negative 8. It doesn't look like that's it though. Is it? Maybe that's the other one. Maybe that's the 1 comma negative 3, 1. No, I don't see it. I must have calculated incorrectly. Oh well, we'll live. It's somewhere right there. Anyway, the point is the surfaces look like the things are showing the types of critical points we are finding here, right? That's the whole idea. What time is it? Okay, sure. Let's see. Do I have other examples I feel like they're important to show you, or we should probably do the other thing. Sorry, one moment. Let me look here real quick. Yeah, that's fine. Sorry, give me one moment to think about this. Yeah, that's sure, sure, sure. No, okay. Yeah. So let's go ahead and talk about kind of the other part of this, which is, yeah. Sorry, so there's kind of two things. I'm looking at your homework assignment here has some of these maximum and min problems. They're not too bad. And then there's some optimization problems, and there is finding an absolute maximum minimum problem. But yeah, it's interesting. This homework is due like I think on the 22nd, so a week from yesterday, but your exam is on Monday and it's covering some of this. Okay, great. Thank you so much. That's excellent. So I guess we don't actually need to do that. Okay, cool. Then let's spend a little more time doing content similar to the first four problems. So let's see, where'd you go? Problem I was looking at. You're fine. So why don't you all give this one a shot? I'm gonna let you work this one fully on your own. So your function, f of x, y, is equal to 2x to the fourth minus 4xy plus y squared. And so I want you to find all the critical values and then test them to see if they're maxima, minima, or saddle points. And this one definitely is kind of more similar to the problem we did before the previous problem where we had like y equals x cubed and x equals y cubed and we had like plug one thing into the other thing to help solve it. It's more like that one. So I'll give you guys like 5 minutes to work on this, and I can even walk around and be helpful if you have questions. Or I can just stand in front awkwardly. Well, I should pass around the. I'll wait to pass around the test one after you guys work on it. You want to check your work? I've done a little bit of it so far. Let's walk through what I've written so far and make sure we're all on the same page. So set the partial is equal to 0. My fx partial was 8x cubed minus 4y. My fy partial was negative 4x plus 2y equal to 0. I decided I was going to work with the one that felt easier to me. And typically that's the one that has like things that are linear or certainly lesser powers. But if you're looking for the easier thing, you're not sure, try picking the thing that has lower powers of x and y. It's usually a good bet. I decided to isolate. So I could have picked either X or Y here. Picking Y is the better choice for two reasons. One, if I isolate X, I'm going to have fractions, which I never want to have fractions if I can help it. And two, I'd much rather plug back into the Y to the first thing than to the X cubed thing. It's just kind of a better choice in that way. But if I had gone the other direction, it still would have worked out just fine. So you can actually pick either one here. So I plugged in Y equal to 2X for Y here, and I end up getting 8X cubed minus 4 times 2X. And then I multiplied it out. I got 8x cubed minus 8x equal to 0. And then I factored out the 8x. I was left with x squared minus 1. I could have factored that further as x minus 1 times x plus 1, but I felt like I didn't need to. I can see from here that either x equal to 0, x equal to 1, or x equal to negative 1 are the solutions to setting that equation equal to 0. Now, again, each of those values for x only give us one half of a critical point. We have to go back to the other equation or the relationship between x and y that we found to find the other half of each of those critical points. If x is 0, y is going to be 2 times 0, which is 0. If x is 1, y is going to be 2 times 1, which is 2. And if x is negative 1, y is going to be 2 times negative 1, which is negative 2. So we get these three critical points: 0, comma 0, 1, comma 2, and negative 1, comma negative 2. Question, yeah. Mm-hmm. Typically, yes. So if you're getting if you're setting one of your partial derivatives equal to zero and getting a getting a value for x or y from that equation equal to zero, well, then you have to plug whatever that solution is into the other equation. Say, okay, well, this value of x made the first equation equal to zero. If I plug it in the second equation, I also want that second equation to be zero. I already know what x is going to be, but now I have to find what y needs to be so that not only is my first equation equal to zero, which we already got by plugging in x equal to whatever it was, my second equation also has to be zero. So exactly, right? We know here that plugging zero into this, that's interesting. Yeah. So, right. And here it's even like, so in some, like in the previous one we did, plugging in zero to the first equation made it true, right? The whole thing, or I forget which one it was. Plugging in zero to the, yeah, let me check here. Right, like plugging in y equal to zero in the second equation just made it zero, no ifs, ands, or buts. Here, we've got actually kind of two things going on at once. If I look at this first equation here, I know that I'm getting x equal to zero. But what's really happening is I'm getting x equal to zero, but I also know that y has to be equal to 2 times x, right? That's the only way this is going to work. So when x is zero, y also has to be zero, and I'm getting 8 times zero minus 4 times zero equals zero. I already know it's going to work over here because essentially I'm saying, oh, well, if x is zero, y has to be zero. Or if x is zero, y has to be zero. So that's how I'm getting the y value. Then it was also making this work. You're welcome. Okay, let's do the other part of this, which is testing to see what we've got. So let's calculate capital D. And I do think you all should do this on your own. I'll remind you that we've already found that the first partial is 8x cubed minus 4y for the partial with respect to x, and my first partial with respect to y is negative 4x plus 2y. So go ahead and write out your capital D and then test all three critical points. 24x times 2. Did I make a mistake? I might have made a mistake. Yeah, it should be. Thank you. 24x squared. Good call. Yes. Right on. Something interesting here that I'll point out. The fact that fyy is always equal to 2 means that if our d is positive, our second derivative is going to have to be positive, meaning any maximum or minimum is going to have to be a minimum. This function cannot have a maximum because your fyy is always positive. So the only types of critical points we're going to get here are saddles or minima, no maxima. We don't need to know that, but it's just kind of interesting to observe. All right, let's go ahead and see what we got. So our capital D is equal to 24x squared times 2 minus 16. So plug in 0, 0, we're going to get 0 times 2 minus 16, which is negative. So that's going to be a saddle at 0, 0. If I plug in 1 comma 2, I'm going to get 24 times 1 times 2 minus 16. That's certainly positive. And since either fxx or fyy is showing as positive, we know we're going to have a minimum. fxx is positive. That means we're concave up. So we have a minimum at 1 comma 2. And I wouldn't be surprised if the other value gives us the same result. Oftentimes, when you have like critical points that are kind of like the same as each other or opposites of each other, or like it's like a 1, 2 and a negative 1, positive 2, if that happens, you often end up with the same either they're both going to be saddles, or they're both going to be maxes, or they're both going to be mins, or one's a max and one's a min. But rarely is it ever like 1 comma 2 gives you a max and negative 1 comma 2 gives you a saddle. That kind of thing just doesn't really happen because of the way these equations typically work. Anyway, plugging in negative 1 for x, we're going to get 24 times 2 again, minus 16. Still positive. Our fxx is still positive. Our fyy is still positive. So same result. Also a minimum at negative 1, negative 2. Cool. Let's go. Oh, let me remember to pass around these. And let's look at one more, and then we probably will talk about the other stuff because eventually you will have to do it, so we should talk about it. So, one more example here. Yeah, let's say our function, do I have a number here? Do I have a number here? 3, 4. Sure. I'm trying to number things occasionally, and sometimes I remember. Okay, number 5. So for number 5 here, let's say we have so I will point out this function, this example I'm making up is similar to your 4th homework question because I thought it was worth doing one like this. Let's say we have e to the negative 6x squared minus 3y squared. And we're going to try and figure out what's going on here. Yeah, that's interesting. Okay. So usual process. My partial with respect to x is going to be, okay, so as a reminder, the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which in this case is going to be negative 12x. And similarly, my fy is going to be e to the stuff, so e to the negative 6x squared minus 3y squared times the derivative with respect to y of that exponent, which is negative 6y. And we say each of these equal to 0. Well, technically you have to say each factor equal to 0, but we want to remind ourselves e to the anything is always positive. We think about the graph of e to the x, right? It has a horizontal asymptote at 0, but it's never equal to 0. So this part, this e to the something is never going to be 0. So really we're just left with negative 12x equaling 0, which means we're going to get x equal to 0. In a similar way, this equation is only going to give us y equal to 0. So here we're in a much simpler situation where our only critical point is 0, comma 0. That's the only value of x and y that's going to make both of these equations equal to 0 at the same time. Now for the fun part. And by fun, I mean not fun. We have to find d, and finding the second partials here is kind of annoying, but we got to do it. So let's find d, fxx, fyy, minus fxy. So we're going to get, let's see here. So fxx, we have to use the product rule. It's going to be e to the stuff. So it's going to be the derivative of this first part, which is the e to the negative 6x squared minus 3y squared times negative 12x. That's the derivative of this, and then we have to multiply it by the other piece not differentiated. Plus, then we switch it, and we say, okay, we're going to leave the first part alone and get e to the negative 6x squared minus 3y squared times the derivative of negative 12x, which is negative 12. That's my fxx. Great. Times, so let's put some brackets around that. Now, the good news is fyy is pretty much the same thing. fyy is going to be, I'm trying to make it look a little bit less lengthy here. e to the negative 6x squared minus 3y squared times negative 6y times negative 6y plus e to the negative 6x squared minus 3y squared times negative 6. Goodness gracious, it's terrible. Minus fxy squared. Fxy is at least a little bit less terrible because we don't have to use the product rule here. If you take your derivative already with respect to x and take the derivative of this with respect to y, we don't have a product of variables anymore, right? We have a function of y times a constant. So the derivative of this with respect to y is going to be e to the negative 6x squared minus 3y squared times the derivative of that, which is again a negative 6y, and then that negative 12x is still hanging out there. Okay, here's the good news. Plugging in 0, 0 is going to make this much, much, much less terrible. So if we plug in 0, 0, I'll remind everybody that e to the 0 is equal to 1. So we're going to get e to the 0 times 0 times 0 plus e to the 0 times negative 12 times, so there's my fxx right there, plugged in, with 0, 0 plugged in. And then times, let's see, we're going to e to the 0 times 0 times 0 plus e to the 0 times negative 6 minus e to the 0 times 0 times 0. Oh, squared. Okay, so the derivatives were terrible, but plugging in the 0, 0 is really not terrible at all. So here we're going to get negative 12 times negative 6 minus 0, so that's going to be positive because it's a negative times a negative. So we know it's positive, meaning we either have a max or a min, and since our fxx is negative 12, we know we are concave down, so we have a maximum at 0, 0. An interesting side note here is that you might have been able to convince yourself that we had a maximum there without doing any of this work. Here's what I want to point out. If you rewrite this as e to the negative 6x squared plus 3y squared, 6x squared plus 3y squared is always greater than or equal to 0 for any choice of x and y. And the only choice of x and y that makes it equal to 0 is 0, 0. If you pick anything else for x and y, you're going to get e to a negative number. And e to a negative number is smaller than e to the 0th power. So e to the 0, which you get by plugging in 0 for x and 0 for y, gives us an output of 1. And any other choice for x and or y is going to give us a smaller output, which means that has to be the maximum. Now, should you do it that way? No, not at all. But just kind of interesting to see that you can kind of convince yourself. Oh, yeah. And it kind of looks, I feel like this one kind of looks like a 10. I mean, I guess I could show you the graph because why not? I think the graphs are fun. So this one looks like, wow. Where did my cursor go? Sorry, it's over there. Cool. So if we graph this one, let's see, what was e to the negative 6x squared plus something y squared plus 3y squared. I need a z equal to, sorry. Do I need a z equal to? Oh, no, I guess not. So you can kind of see it, right? It looks like, oh, wow, that's not what I meant to do. I meant to do that. I meant to do that. There you go, right? Yeah, that's the worst. I'm not a fan of this color. Let's pick any other color. Yeah, great. Cool. All right. So you can kind of see, oh, yeah, it looks pretty flat. And then it has a little peak in the middle there. Kind of like the e to the x, right? The e to the negative x part of the e to the x function like does that. It's kind of like we've got all that, but in every direction like that. So kind of cool. Sure, 107. So there's one other thing I'll point out. I don't think your instructor would ask you a question like this on an exam, but I think it's worth spending a few minutes on just to kind of point out how something else can happen. So let's look at a couple more examples just to say a few words here. So let's say you had this function, f of x comma y equal to x squared times y to the fourth. In fact, why don't you all go ahead and find the partials and find your only critical point. Yes, there's only one critical point. Our fx is 2x times y to the fourth. Our fy is x squared times 4y cubed. And it kind of looks like, well, let's see here. We're either going to get x equal to 0 or y equal to 0. And I don't think there's really, that's actually, just interesting. So how many critical points do we have here? I know I said one, but I think I was wrong. I think this is, this one's kind of annoyingly interesting. So certainly 0, 0 is a critical point, right? Let me ask you just, this question is probably not super important, but just for thought, so this is a critical point. What about 3 comma 0? Does that make both of those equations equal to 0? If x is 3 and y is 0, is this first equation equal to 0? Is the second equation equal to 0? Yes. So accidentally here, I actually picked an example that doesn't have one critical point. It has an infinite number of critical points. Every point on the x-axis and every point on the y-axis is a critical point. It's a point that makes both of those derivatives equal to 0. Right? You could pick a critical point that's any x value and y is 0, or you could have a critical point that is 0 for x and any y value. So really, there's lots. Now, here's the more annoying part. If we find our capital D, our fxx times fyy minus fxy squared, let's take a look and see what that's equal to. Well, let's see. Our fxx is going to be 2 times y to the fourth. Our fyy is going to be x squared times 12y squared. And our fxy is going to be 2x times 4y cubed squared. And notably, if I pick just x equal to 0, I'm going to get a 0 here and a 0 there. Or if I pick just y equal to 0, I'm going to get a 0 here and a 0 there. And if they're both equal to 0, I'm also going to get 0. So any choice of any of these infinite number of critical points, no matter what we plug in, d evaluated at any critical point is going to equal 0. And I know we haven't really reflected on this very much, but if capital D is neither negative nor positive, that means the test is inconclusive. We don't know whether these critical points, at least based on this test, we don't know if they are maxima, minima, or saddle points. Except we do. We just don't know we know yet. Here's how we know. This function, x to an even power times y to an even power, is always going to output what kind of numbers? Positive. Actually, technically non-negative, right? Because you could get 0. But no matter what we plug in, you can't get a negative number out. So the smallest number we can get out is 0, meaning each of these critical points that gives you a value of 0 is a minimum. So all of these critical points are minima. Okay, this one's kind of weird looking. So what it kind of looks like is, no, I can't even describe it with words. I just have to show you. But it really does do the thing we say it's doing. If you graph z equal to x squared times y to the fourth, look at that. You've got this thing that's like kind of it's like sitting on the x and y axis, and all of the points along the x and y axis are have a z value of 0, and then everything off of that, if you zoom in a little bit, stop moving. If you zoom in a bit, you can really see, oh yeah, look, they're really, really close to 0, but they're not actually 0 until you get to the x or the y axis. So sometimes you can determine whether something has maxima or minima not based on using capital D equal to fxx times fyy minus fxy squared, but using the fact that you can observe, oh yeah, well, this function is always not negative, or this function is always not positive, and so the values you're getting are either the max or the min. But again, I don't think that's really a great test question. So I wouldn't worry too much about that kind of thing happening. All right. So here's what's coming up next after this material. There's two things. I think we should talk about the easier thing, which is the easier to understand thing, which is optimization, which is really just an application of what we're doing already. So optimization, the hard part about optimization isn't finding all the critical value stuff. The hard part is setting up the equations you need in the first place. So let's look at kind of a typical example. By the way, this optimization process is very similar to what we did in 17A, where like you'd be given some function you want to either like maximize or minimize some like volume of a box or whatever. And then you have some constraint like the box has to have this much surface area. Except now we have more variables in place. So here's a similar example, but with more variables. Um, we want to make a box. We want to make a box without a lid. I don't know why you wouldn't want a lid, but that's what this person wants. That holds 32 cubic feet of volume. And we want to use the least amount of material possible. Which, when they say the least amount of material, they mean minimize the surface area, right? Because the surface area is the material dimensions. So I would always recommend for a situation like this, drawing some sort of picture. And unlike when we did this in 17A, in 17A, typically we say we have a box with a square base so that we didn't have too many variables going. Here, that's not going to be the case. Our base could be some sort of rectangle. It doesn't have to be a square where both dimensions are the same. So we have some sort of boxy shape with no top. So there's my box. And we're going to label the dimensions. Let's call the base X, the depth Y, the height Z. And as will typically happen with this, you're going to have two equations. One thing you want to maximize or minimize or optimize in general, and some constraint. So the thing we're trying to optimize is what? What are we trying to maximize or minimize here? The volume or the surface area? Right. One way you know what it is it's the thing that's not already equal to a number. They already told us exactly what the volume is going to be. There's no way of maximizing, minimizing the volume if they said it has to be 32. It's just 32. So we want to optimize the surface area. And the surface area equation is, well, it's all these areas of rectangles added up together. So it's the bottom rectangle, which is x times y, so it has an area of x times y, and then the front rectangle here, which is x times z, plus the back rectangle, which is also x times z. So I have 2 times x times z. And then the left rectangle, which is y times z, plus the right rectangle, which is also y times z. So 2 times y times z. And similar to in 17a, how we had a function of 2 variables and that was too many, here we have a function of 3 variables and that's too many for us to deal with. We can deal with, as you just did like 4 or 5 times, finding the maximum of a function of 2 variables, but any more than that is too many. So we're going to use our constraint. Our constraint is that the volume, whose equation is x times y times z, has to be equal to 32. And then you're typically going to take this constraint equation isolate one of your variables and then sub that back into the other equation so that your other equation then has one variable eliminated and you're left with two variables. And then we can apply the process that we just did 5 times to this new thing. So the standard choice is to solve for z, unless there's a good reason to pick something else. Here, it doesn't really seem like there's a good reason to pick any one thing over the other. The only thing I point out is Z looks better because it kind of shows up in the same way, whereas X and Y kind of don't. But really, you could make any choice you wanted here. So we're going to say that Z is equal to 32 divided by X times Y. And then we're going to substitute that in to each of the Z's in our thing we want to optimize. So now our surface area is going to be a function of just X and Y. And it's going to be X times Y plus 2 times X times 32 over X times Y plus 2 times Y times 32 over X times Y. And it is definitely in your interest to simplify this equation before you start taking partial derivatives. So we're going to make this much easier to deal with. We're going to say that f of x times y, f of x comma y is equal to x times y. The 2 times x times 32 over x times y, the x's cancel. 2 times 32 is 64. And dividing by y, I'd rather write multiplying by y to the negative 1. Similarly here, I get 64 times x to the negative 1. And I'm going to make an observation here that I made before. This function of x and y is symmetric in x and y, right? If you interchange the x and the y's, you'd still get the same exact equation. So we're expecting in this problem for x and y to probably be equal to each other. Okay, doesn't seem unreasonable. So now we're going to find the critical points in the usual way. So find the critical points by taking each partial derivative and say, oh, what the heck? Oh, I forgot to plug in my computer. That's terrible. Let me plug it in real quick. About that over here. Bummer. Hate when you do that. Ugh. Okay. Safe. All right, good. Okay, so right, our partial with respect to x is going to be y plus 0 plus negative 64 times x to the negative second. So minus 64 x to the negative 2. And similarly, our fy is going to be x minus 64 times y to the negative second. Solving this is not my favorite. How would I want to, what would I really do? I'm trying to like I know I can solve this like in kind of a long, protracted way. I'm trying to think to myself that there's like a faster way to deal with this. Don't think there really is. So here's what I would probably do. I would write this one as y equal to 64 over x squared. This one as x equal to, yeah, 64 over y squared. And I don't like it, but you kind of have to take one of these and plug it into the other one. So I'm going to take this and plug it in for y down here. Gross. So that's going to give me x equal to 64 over y squared squared. Let's make that better. That's going to be, instead of 64 divided by a fraction, it's going to be 64 multiplied by the reciprocal of that fraction. So instead of 64 squared over y squared squared, it's going to be y squared squared over 64 squared. It's still not great. I feel like I'm doing something stupid here. I am doing something stupid here. Yeah, I was plugging in 64 over x squared into y squared, so that should be an x, not a y. Let's not try to squeeze this all in here. Let's give ourselves more room to work with because we have plenty of paper. So looking at this again, I was taking my y equal to 64 over x squared, and I was substituting that into the equation x equal to 64 over y squared. So that's going to go in for y right there. So we're going to get, let me write this the correct way this time. X equal to 64 over x, geez, try to be correct. Yeah, thank you. 64 over x squared squared, which again, we're going to rewrite this as x equal to 64 times the reciprocal of that. X squared squared over 64 squared. One thing nice happens, the 64 cancels with one of those 64s. I would probably multiply both sides by 64 and say 64 times x is equal to x to the fourth. Here, even though it's probably not the best thing to do, you could get away with dividing by x. Here's why. Is x equal to 0 a solution to this equation? Yes, it is. Is x equal to 0 going to be the value that minimizes the surface area and still gives you a volume of 32? Absolutely not. In fact, it would be appropriate to say that x equal to 0 isn't in the domain of this situation because you can't have a box with a volume of 32 and have one of the dimensions be 0. So it's probably fine to divide by x here, which is kind of the thing I was alluding to earlier when I said we don't usually divide by a variable, but occasionally it's okay. Here's one of those situations where it's really kind of okay. So we get 64 equal to x cubed, and we're going to get x equal to 4. Go back and plug that in to find y. And not surprisingly, y is going to be 64 over 4 squared, which is going to be 4 as well. Do we need to check to see that this is what we actually think it is? It's probably not a bad idea. So let's go ahead and find our capital D, which is equal to fxx, which is going to be, let's see, fxx is going to be 128 times x to the negative third. Our fyy, which is going to be 128 times y to the negative third, minus our fxy, which is going to be 1 squared. And if I plug in 4, if I plug in 4 comma 4, I'm going to get 128 over 64 times 128 over 64 minus 1, and that's going to be positive. And since my fxx is also positive, I know I have something that is concave up, which means I know I have a minimum. And I probably didn't phrase this question particularly well, but what I should have asked is find the dimensions to construct a box with a volume of 32 cubic feet and a minimum surface area. And if I'm answering that question, I haven't quite finished it because while I have found the x and the y dimensions, I still have to find the z dimension. So I'm going to go back to what I found for z. And if you remember, it was z equal to 32 divided by x times y. If we plug in 4 and 4, we're going to get z equal to 32 divided by 4 times 4, which is 2. So the dimensions of this box are 4 feet by 4 feet by 2 feet high.